Hello, everybody. I'm your host, and today our speaker is Lorenzo Gavassino from Nicolaus Copernicus Astronomical Center of the Polish Academy of Sciences, and he's going to talk. He's going to give us a new perspective on an old problem, and with that introduction, I need to ask you if you have a question. You can type in the chat or you can raise your hands so you can ask questions during the talk, but please keep longer questions or discussions to the end of the talk. So please, Lorenzo.
So here I have some interference, but I hope that everybody can hear me. I cannot hear anymore Masoud, but I think I can start. Okay, perfect. So if everybody can hear me, if you don't, just write it on the chat or you can speak. It's completely fine. So if I can, maybe now I will start. So good afternoon, everybody, or morning or evening, depending on where you are. I am Lorenzo Gavassino, third year PhD student at the Nicolaus Copernicus Astronomical Center of Warsaw. And the work I'm going to talk about is this one. You can find the title, the link, and so on also in the description of this talk. Yes, this is a chat. Okay, I can turn off the video camera. No problem. Okay, so my talk will focus mainly on this work that has been done also in collaboration with Dr. Marco Antonelli and Professor Brynmore Haskell, who is my supervisor. But I would like to give you a broader perspective than what is inside the paper. Of course, the paper will be the center, the core of the presentation. But for those of you who are not maybe so familiar with the topic, if there is somebody who is not familiar, I would like to give first a general introduction on the problem, and I would like also to give it in a way that is not so conventional, in the sense that I'm going to deal with this problem in a way which is not usually presented in the when you hear about these problems. So the topic is dissipation in relativity. For simplicity, it will be special relativity, but that's just for the comfort of the calculation, to simplify the notations and the presentation. The curvature of space-time does not change much in what I'm going to say. So the idea is that I will talk about the famous problem of the instability of the relativistic Navier-Stokes equations. And however, I will try to address it in a new way, which is in the end the essence of my paper. So this said, let's start. Okay, does it? Okay, it works. So let's start with an equation that we all know and we are familiar with. This is the standard Newtonian equation for the diffusion equation. This is the equation which governs the evolution of the temperature field. Now we work in one dimension, 1 + 1 if you want. And you can think of it as the equation which governs the evolution of the temperature along a metal bar. You can consider a one-dimensional infinite metal bar. You define the temperature as what the thermometer would measure if you put it on a particular point of the bar. So it's a field, and its evolution is governed by this equation, which is very well known and comes directly from the Fourier law. So if you look at this equation, this is important, you will see that it's of the second order in space and of the first order in time. Now, the fact that it is of the first order in time means that you only need to give me an initial profile for the temperature. Here you can see an example. I just chose something that looks aesthetically pleasant for me. You can take whatever profile you want, and then you switch on time, and you have all the information you need. The profile is enough, and your equation will tell you how the system evolves. In particular, if you wait a bit, you will see that very fast this equation smooths out all the wedges and makes everything smoother. And this is the typical behavior of diffusion. In the end, it will try to make things as smooth as it can. And during the evolution, you will see after a while, everything tends to go to a homogeneous configuration. Now, the question that now we want to answer is, does this equation work in relativity? There is a first problem, which is very well known. It is the problem of causality. In essence, if you compute from this equation the green function, you will see that it is a Gaussian. And the fact that it is a Gaussian implies that the green function has infinite tails, which means that if you imagine to put a bump of energy in a point, located in a point, a Dirac delta of your temperature, and you switch on time a bit and you let the system evolve, immediately after the instant in which you have put your temperature here, everybody in the universe is going to detect a small part of the tail of this distribution. So I put some energy here and say in the Andromeda galaxy, people are going to detect something. This is of course a problem. It's against causality, is a causality violation because the information that I have put the energy here propagates outside the light cone. You know, this is very well known, but it's not the real big issue with this equation, because in the end we know that this equation is just an approximation. So as long as we deal with solutions which have very small tails, one can say, okay, it's fine, it's just an approximation. Why is it that bad? Well, the fact is that there is a bigger problem that this equation has in relativity, which will be actually the real focus of this presentation. And this is the famous instability problem. Let me explain it fast. So the idea is, let's take this equation and we ask, what happens if we boost them? So if we look at them from a different reference frame, in this case, since we are describing the evolution of the temperature along a metal bar, you can imagine that you set this metal bar into motion and you look at how the temperature profile evolves from the point of view of somebody who sees this metal bar moving. Now, before someone gets scared about the possibility of applying also a transformation to this T, I am defining temperature as through this equation where this is the temperature covector. So by definition, I am considering it a scalar field. And so there is no issue. I do not need to put gammas here or there to transform this temperature. I just treat it as a normal scalar field. And I'm just boosting the equation that it obeys. Now, here you immediately see what happens when you make the boost. You need to apply this coordinate transformation, and you see that the derivative in time becomes a linear combination of derivatives in time and space. And this is not a big deal. It happens the same also in Newtonian physics. But the real novelty that special relativity introduces is that the derivative in space gets mixed with the derivative in time. And in particular, you notice that suddenly you are creating a second order derivative in time, which has no Newtonian analog. So why is this second derivative in time a novelty? Why is it important? Because if I have a first order equation in time, then to give completely information about my initial conditions, I only need to give the profile of the temperature. But if my equation is of the second order, knowing the temperature everywhere is not enough. You also need to give me at least the first order derivative in time of the temperature, because the equation is of the second order. So my boost somehow has created new degrees of freedom in the new reference frame. If you tell somebody the temperature everywhere and this metal bar is moving with respect to this person is not able to solve the equation, needs more. Now, why does this really change the things? It changes them because let's make this experiment. Let's look for homogeneous solution of this equation. So we imagine that our solution depends only on T prime, homogeneous solution in the reference frame, in the boosted reference frame, in the reference frame in which the metal bar is moving. So in this reference frame, we need to kill the space partial derivatives, and our equation becomes this. And of course, if you solve it, you need to give me two initial parameters for the solution, which is the value of the temperature in the initial state and the value of the time derivative of the temperature in the initial state. And these are all the solutions that you find to this equation. And what you discover is that if you set this derivative to be not zero, then you have this part of the solution which is exponentially growing. And it's often exponentially growing quite fast. So what you observe solving this equation is essentially a thermal runaway. A temperature we start with a given value and then grows very fast in time. It's essentially an explosion. And you see that this possibility, this runaway exists only because I'm free to set this parameter as I wish. The reason why this runaway does not exist in Newtonian is that since I have not this second order derivative in time, then I'm not able to set the first derivative in time as I wish. And so in Newtonian physics, this solution does not exist. The problem is that in relativity, not only this kind of solution exists, but if you want to have the analog of your Newtonian solution without this explosion, you need, okay, I see that there is a raised hand. So you can speak?
Hello, do you hear me?
Yes.
I want to say a point, and that is in your derivation, you assume that the temperature itself is a scalar field. Yes.
Yeah, I define it in this way.
So I mean, by the boost transformation, temperature doesn't change anymore. Yes.
If you define the temperature as the inverse of the length of the temperature covector, which we know is a 4 vector, then if you define the temperature in this way, then you don't need to apply any transformation because it's a scalar by construction. If instead you don't define it in if you define it in a different way, for example, the inverse of its 0th component, then you get a gamma. This equation remains this equation because the gamma is a constant, given the fact that you have a fixed for velocity for your metal bar. So this is not going to be an issue.
Okay, thank you.
Is it okay? Okay.
Thank you.
So thank you for the question. Always feel free to ask. You don't even, I think you don't even need to raise hand. Just make your question and interrupt me. I think it's more efficient. Okay, so I was saying, what I was saying is that from the fact that I'm able to set this parameter free, I create this runaway. The point is that if I don't want to have it, I need to set an initial condition, which is a subset of measure 0 in the space of my possible initial conditions, because my possible initial conditions define a 2-dimensional space, in this case, for the homogeneous configuration, and I need to pick an exact 1-dimensional submanifold of this space of initial conditions. So this is the real problem. Now the question is, how can it be that in the reference frame in which the bar is moving, I have an instability, while in the original reference frame, I didn't have it? What's happening? Because an instability should be something that everybody sees. Well, the interesting thing is that here I'm working with homogeneous configurations. If I take a homogeneous configuration and I try to boost it back in the original reference frame, now due to the relativity of simultaneity, what is homogeneous in a reference frame but evolves in time is no longer homogeneous in another reference frame. In fact, these solutions flowed, if you go back in the original reference frame, describe a profile which is not homogeneous. And in particular, all these crazy solutions in which this is not zero have a behavior of this kind, which means that your initial profile in space is an exponential. So you have a temperature which goes to infinity as x goes to minus infinity, if you take v to be positive for simplicity. And your solution is actually this exponential, which is shifting faster than light. So these kind of solutions, when you set these non-zero, are clearly something which is absurd in the original reference frame. They are strongly acausal because you have energy which is shifting faster than light. And you have infinite temperature as you move to minus infinity. So it's an initial condition you would never pick up if you were in this reference frame. And of course, they are incompatible with all the assumptions that you make to derive these equations in the first place. Because when you derive this equation, you assume that the temperature is not infinite, that your evolution is low. There is a set of conditions that you derive from kinetic theory. It's clear that all these solutions don't make any sense physically. But the problem is that to avoid them, when you work in the boosted frame, you would need to fine-tune your initial conditions. So it's really a problem of well-posedness of your initial equations. If you want to know the mathematical details said in a more rigorous way, talking about well-posedness and so on, I kindly suggest you to look at this paper, which is very clear and really explains what is going on. What I've done now, I was talking about the homogeneous situation, but you can also go in the Fourier space, consider situations which are not homogeneous, and the conclusion is essentially the same. So this instability problem tells you that it's not really the equation that is a problem. The real problem is that you would need to fine-tune your initial conditions working in an arbitrary reference frame to obtain solutions which are meaningful. And this makes this equation essentially useless if, for example, you want to simulate. If you want to make a simulation, you cannot hope that your equations cannot require such a detailed fine-tuning to be solved. This is what happens for your diffusion equation. Now let's move more concretely to the hydrodynamic equations of Navier-Stokes, which is really what we're interested in. What I'm going to show you is that the problem is essentially analogous to the diffusion equation. So the diffusion equation was a toy model, but it's not so different from what happens here in the relativistic Navier-Stokes. And the mathematical origin is really the same. I will consider, for simplicity, the Eckart approach to dissipation. Now, maybe you know that there is also the Landau-Lifshitz approach. There is really no difference in the conclusions. I will talk about Eckart because it's, if you want, the one which more reminds the standard Navier-Stokes, but also the Landau-Lifshitz reaches exactly the same result. So the idea is that in a dissipative relativistic hydrodynamic theory, you need to give a stress energy tensor, and you give it in terms of a perfect fluid part plus a non-equilibrium part, which contains the heat flux and your viscous stresses. And if you are in Newtonian physics, you have also this prescription for these things. Now, clearly, you need to move to relativity, so you need to change something here. And the idea of Eckart, well, Eckart uses a particular procedure that I'm not going to present to you, but in essence, the result is that all these relations, these Newtonian relations in the Eckart theory are exactly the same if you look at them in the reference frame of the fluid element. So if you choose a reference frame in which this is collinear to the derivative with respect to time. Apart from this piece, okay, sorry. Apart from this piece, which is a piece that you find which contains this acceleration, which comes from the fact that energy flows are also momentum densities. So when you have your heat, you have also a flow of momentum. Even if you forget about these things, in the end, basically, you take your Newtonian equations and you assume that they are still true in the reference frame of the fluid. Now what happens? Again, analogously to the diffusion equations, you take these relations, you boost them. Again, your derivative with respect to space is mixed with the derivative with respect to time. And so, for example, your bulk viscosity, which in the reference frame of the fluid has only spatial gradients, gets also a time derivative. So as you see, the stresses, which in Navier-Stokes were only proportional to spatial gradients, now get also a time derivative. Now, when you write your equation of motion is simply a conservation of the energy momentum, and this in turn has another derivative. So you will have a time derivative which will act on the pi, and so will act on this time derivative. So again, you are producing a second derivative. And this is a second derivative which does not exist in Newtonian. Navier-Stokes does not have this second derivative. Navier-Stokes has only first derivatives in time. And it's only a result, if you want, of the relativity of simultaneity. So this is the reason why this kind of effect does not appear in Newtonian. You have one second derivative which is not there in Newtonian. So what happens now if you try to solve the equations? You can do something analogous to the case of the diffusion equation I presented before. Now you can work with the linearized problem just because it's simple. You take your general solution and you assume that there is an equilibrium solution plus a perturbation. You expand in Fourier your perturbation, and then you study your dispersion relations. And your dispersion relations give you information about the speed propagation and the stability of your solution. Now, in the standard Navier-Stokes, if you solve them, you will find that typically you obtain two kinds of solutions. You obtain typically the sound waves, which this is the speed of sound, they are proportional to the gradient in the end, to the k. And you have an imaginary part, which is the damping of the sound waves. And this is a true damping because you can compute it in Navier-Stokes and you will find that this quantity is positive. So you know that these modes decay. And it's correct. As we know, sound waves after a while are dissipated. They are damped. And you have also the shear waves, which have this kind of dispersion relation. All these waves have the property that they are stable and they are gapeless. Gapeless means that in the limit in which k goes to 0, also omega goes to 0, which basically tells you that in homogeneous systems, you don't have hydrodynamic evolution. Hydrodynamics describe the evolution of the gradients. So if the system is homogeneous, you don't have any evolution. Now, the problem is that since you have this second derivative, you have more degrees of freedom, you have more possible initial conditions, analogously to what we saw in the diffusion equation. So this creates new modes. And these new modes are gapped. Gapped means that even in the limit in which k goes to 0, you have that your omega can be non-zero. And what you discover is that these gapped modes actually are unstable. They grow with time, analogously to what we saw in the diffusion equation. So these gap modes exist because of the higher ordering time of your equations. And they exist, and they are an evolution of a system which exists even in the homogeneous limit. This is why we say that they are gapped. If they were gapless, then this omega would go to 0 for small gradients, but they don't. Now, what I have presented up to now was really from the point of view of somebody who is trying to solve some differential equations. And all these things that I have presented to you up to now were quite well known in general. But we were not completely happy with these explanations because something really strange is happening in this system. Because if you think about it, dissipation is what should drive system towards equilibrium, not far away from it. So it's really strange that adding dissipation to your equations, the system is going away from equilibrium instead of converging to it. So if you don't look at the system just from the point of view of somebody who is solving your equation of motion, but you look at it from a thermodynamic point of view, immediately you see that something is wrong. Because you know from general principles that every thermodynamic system meets a maximum entropy state. Since the entropy can only grow, the system, after a while, after some evolution, must necessarily go to this maximum entropy state, because to go away from it, you should make the entropy decrease. So evolution should go there. And this state is what you define as your thermodynamic equilibrium, and it's necessarily stable under perturbation. This is the famous Lyapunov criterion for stability. Because if you want to perturb your system and you move just a bit from the maximum, the system cannot go away, because to go away, you would need the entropy to go down, but the entropy can only go up, so the system can only go back. So system which is in true thermodynamic equilibrium can never be really unstable. Instability is also in physics, in every context of physics, when you find an instability of a system, it comes from the fact that this system is not really the true global thermodynamic equilibrium. It's just an unstable equilibrium state. This is really the definition, a system which is not the real maximum entropy state. So what is going on in the Eckart theory and also in the Landau-Lifshitz, if you prefer the Landau-Lifshitz, what is going on in these theories? What is violated here? For sure, you are not violating the increase of the entropy, because both Landau-Lifshitz and Eckart ensure that the entropy grows exactly. So something else is happening. And now we come really to the essence of our paper, because our paper now is described in the next 2 slides. These 2 slides are what you should take in mind when you go away. This is the central message of this presentation. So let's see what really is happening. Take the Newtonian Navier-Stokes equations as we know them. Now, the only degrees of freedom are the thermodynamic fields. Let's say temperature, chemical potential, and fluid for velocity. Now, the number of global constants of motion is equal to the number of your thermodynamic fields, because you have energy, number of particles, and momentum. So you see that they are exactly the same. In total, 3, 4, 5. They are both 5. Now, as a consequence, if you fix the value of the global constants of motion of the system, there is only one possible homogeneous state in which you can find the system, which means that you cannot have any kind of gapped mode, because there is only one possible state in which the system can be when it is homogeneous. So there can be no evolution when the system is homogeneous. Now, the total entropy is always maximum in homogeneous states once you make sure that some basic thermodynamic conditions are respected. For example, if you make sure that your specific heat is positive, your sound speed squared is positive. the standard thermodynamic conditions of stability, if you respect them, then you know that the homogeneous state will be the maximum entropy state. Therefore, the hydromodes, and the hydromodes are these modes. They are usually called hydromodes. These are the gapped modes, and these are usually called hydromodes. The hydromodes can only reduce the entropy. If you imagine to take your global thermodynamic equilibrium state and you perturb it, the only way to perturb it is to go outside from the homogeneous state. But doing it, you necessarily reduce the entropy. Evolution makes the entropy grow, and so you will necessarily go back to the maximum entropy state, which will be stable. And this is the reason why Newtonian Navier-Stokes is stable and everything works in Newtonian. However, things are different when you move to relativity. Because in relativity, if you take, for example, the Eckart theory, degrees of freedom now are not only the fields, but also their time derivatives. And this comes from the fact that your equations are of the second order. So you have more freedom in your initial conditions. So more degrees of freedom. Now their number is larger than the number of global constants of motion of the system. So there are many ways in which the system can exist and at the same time be homogeneous. And this is the very origin of the gapped modes. The gapped modes exist because the system can be homogeneous and still can be found in many different homogeneous states. This creates the gapped modes. And the gapped modes are just the evolution of the system through these homogeneous states. Now, the essence of our paper is that if you imagine to put your hydromodes on one axis and your gapped modes on this axis, you always find that the entropy has a profile like this. The entropy is in a saddle, the global maximum equilibrium state is a saddle point of the entropy, is a point where the entropy has a saddle. And the entropy grows along the gapped modes. So this is the real origin of the instability, the thermodynamic origin of the instability of the Eckart theory. It comes from the fact that here you have a behavior which is essentially the Newtonian one. But you have a new axis given by this state space extension due to the existence of these new degrees of freedom. The system will make the entropy grow, so it will move along these paths along which the entropy grows. So this is the origin of the instability of the Eckart theory and also of the Landau-Lifshitz theory. You are describing an entropy that is not maximum in what should be your equilibrium, but at the same time, you are requiring that the entropy grows exactly. So now the question is, how do we solve this? There are two main ways of approaching this problem. There is a way which is, if you want, the historical way. It's the approach that you can find mostly in the literature. It's the approach of the Israel-Stewart theory, and in general of the second order theories, but also of the divergent type theories and the Carter variational approach. And now there is a completely different new approach, which has been designed very recently. And these two approaches try to solve this problem in a completely different way. And these two approaches are distinguished by the answer that they give to a very simple question. And the question is the following one. So we know that the gapped modes exist. They are a mathematical necessity. But should I make sure that my hydrodynamic theory describes them? Or somehow I should just try to get rid of them? So should I expect hydrodynamics to be able to give a good description of these gapped modes? Or should I just find a way to solve this mathematical problem of the gapped modes and forget about them? Now, these new theories, I will call them frame stabilized first order theories. Here you can find the main authors who are working on this. And this is a very new approach. They basically say that these gap modes are unphysical and you should just try to get rid of them somehow. While the standard approach says that you should understand them. These gap modes have something, has some physical insight that you need to understand. So basically, Eckart and Landau-Lifshitz are just describing them wrongly, and you need to improve the description of these gap modes. Now I'm going to present the philosophical essence of these two approaches. I will not present the technicalities, and I'm not going to claim to know how the people who have developed these two theories think. But I really want to analyze these two possible approaches from the point of view of this problem, because these two approaches solve this problem in a completely different way. And I really believe that analyzing these two theories from the point of view of how they solve this problem is really the way to understand where hydrodynamics is going and what we should do in the future. And in part, some of these things have been analyzed in our paper. So let's first with this answer, with the newest answer, the approach of the frame stabilized first order theories. If you want to know in pills what they think, then this sentence is essentially enough. Do you need to fine tune your initial conditions? Because this is what we know. We know that these gap modes shouldn't be there, and we should fine tune our initial conditions to get rid of them. Just fix your equations in a way that they clean these gap modes for you. How is this done? Well, here is the idea. You start from the assumption that hydrodynamics is fundamentally an infrared theory, in the sense that hydrodynamics works only in the limit of omega and k, which go to 0. So the real regime of interest of hydrodynamics is this region in the k omega space. The gap modes are completely outside this infrared limit. The gap modes are fast. The gap modes do not have an omega which goes to 0 as k goes to 0, so they are not in this region. So basically, the gap modes are completely unphysical. You do not need to describe them. The only thing that you need to do is you take this structure, you don't bother of changing the shape of the entropy. The shape of the entropy can still be the same, but you try somehow to build a theory which behaves in the proper way along the traditional Navier-Stokes path, so along the hydro modes. You want the second law to hold along these modes, so you know that your theory will converge to this point, which is your global thermodynamic equilibrium state. And somehow you try to fix your theory in a way that you reverse this path. And even if you must do it at the expense of making your entropy go down, you try to reverse the path of your gap modes, and you try just to make sure that these gap modes die fast. How is this done more in practice? Here is the technique. You take the stress energy tensor and you expand in the derivatives. You make a first order derivative expansion. You say that you have a part which is a 0th order in the derivatives, and is what you call the perfect fluid. And the first order part is what you really call the viscous part. And instead of doing what Eckart and Landau-Lifshitz do, so you make some particular assumption on this part, you just include every possible piece that is possible to include inside this viscous part. You don't leave anything. You put everything you can, of course, compatible with basic covariance requirements. And in the end, you find that you have a dissipative theory which has a lot of free parameters that you can fix. In total, you have 16 free parameters you can fix as you wish. And then how do you fix them? basically you do what you have already planned to do. You study the hydromodes and you fix your parameters in a way that along the hydromodes, you reproduce the standard Navier-Stokes behavior. Basically, you start noticing that along the hydromodes, every theory can be mapped into an equivalent Eckart. And you fix the parameter in a way to reproduce all the coefficients that you want in that corresponding Eckart theory or Landau-Lifshitz, if you prefer. But this will provide only 3 constraints, and still you have a lot of free parameters. What do you do with the remaining 13 free parameters? You do what you want to do. You fix them in a way to ensure that the gap modes are unstable. And to do that, you fix them in a way to break the second law along the gap modes, because you need the gap mode to go down. The only way for the gap mode to go down is that your entropy goes down. So you break the second law along the gap modes just to make sure that they die, and they die fast. And you can do it just fixing your remaining parameter. Then what you discover is that you have still a lot of room, because these parameters are really many, and you can still have the opportunity to fix the remaining freedom that you have, even to ensure causality, and so to fix the problem of the superluminal propagation of things. So with this trick, somehow you are saying, the gap modes are unphysical, I just want them to die fast. And I break the second law of the gap modes on these gap modes, I don't care, because anyway, my gap modes will die soon. You say that after the gap modes are dead, you are on shell. When you set your arbitrary initial condition, you are putting some gap modes there, but these gap modes are unphysical. You wait until they die, then your system is on shell, and that's when your predictions of the hydrodynamic theory is supposed to give you something physical. And everything now should work fine. I just would like to make a general comment, because in these theories, they use the word frame, and they talk about different hydrodynamic frames. What are these frames? I think it's enlightening to think about these frames from this point of view. You say that 2 theories are connected by change of hydrodynamic frame if have the same behavior along the hydromodes, but a different behavior along the gap modes. Now, to see that this is exactly what they mean when they develop these theories, is the way to show this is that when you move from a frame to the other, you are throwing away some second derivatives, but you can throw away these second derivatives only here, only in the hydromodes. Along the gap modes, it's not true that your second derivative is smaller than the first derivative, because this is fine, because omega is finite. So the second derivative has the same order of the first derivative. So this is the reason why different frames behave differently along the gap modes. And along the hydromodes, you can really neglect your second derivative, and so everything is the same. So basically, this is how these frame-stabilized first-order theories work. They admit that when you set your initial conditions, there is a first transient in which you need to wait until the gap modes die, and then the predictions of hydrodynamics become physical. However, you have now, let's move to the second approach, to the other possibility, the way of the yes. Now, in one sentence, the way of the yes starts from the following idea. The gap modes survive even in the homogeneous limit. So they are the evolution of homogeneous system. Therefore, you can see them as thermodynamic modes, because thermodynamics in the end works in the homogeneous limit. And then when you make your non-homogeneous, non-equilibrium thermodynamics, you consider some deviations from global thermodynamic equilibrium. And these deviations typically are assumed homogeneous. And the result of these theories is the so-called extended irreversible thermodynamics. Basically, the philosophy is, I want to have a system of equations which, along the hydromodes, becomes the standard Navier-Stokes hydrodynamics. But along the gapped modes, I want these theories to reduce just to non-equilibrium thermodynamics. So you want to have the standard thermodynamic relaxation of a system towards the global thermodynamic equilibrium as you know it. So the approach of the Navier-Stokes and of the Israel-Stewart theory and in general of the second order theory is to have a theory which is able also to describe the gapped modes. These theories claim that they are able to understand the gapped modes. And these gapped modes are not the standard Navier-Stokes hydrodynamics, but they are pure thermodynamic modes. And I would like to remark that there is no connection in this case with the fact that you have relativity in the game, because the Israel-Stewart theory has a Newtonian analog, and its Newtonian analog is not Navier-Stokes. The Newtonian analog is the Dew theory for the extended irreversible thermodynamics, which has exactly the same behavior. So when they say that Israel-Stewart is just the relativistic generalization of Navier-Stokes, this is a partial statement, because the truth is that if you take the Newtonian limit of the Israel-Stewart theory, you don't recover Navier-Stokes, but you recover another well-established hydrodynamic theory. So what happens now? It happens that if you really want to have an equation like this, then this entropy is absolutely not acceptable, because you want to be able to look at this system as really a non-equilibrium thermodynamic system. And in order to do that, you need to have an entropy which is realistic. And so you need it to be maximum in equilibrium. So you need to include other terms. In particular, you will need to add the second order contributions to the entropy. And these second order contributions should fix the profile of your global entropy in a way to restore the maximum. Now, actually, in our paper, we proved that the stability conditions found by Hitchcock and Lindblom for Israel-Stewart are exactly those conditions which make the total entropy maximized in equilibrium. And you can see it in this plot, which is directly taken from our paper. This plot essentially is the essence of our paper. So here we put on the x-axis the amplitude of the gapped mode k equal to 0. So the amplitude of the homogeneous mode, which is in the end what really encodes the essence of all your problems. And on the y-axis, you put total entropy along this gapped mode. You need to take a prescription for your entropy current. If you take Eckart, then this is your formula for the entropy current. And when you compute your total entropy, you find a profile like this. This is exactly the profile of the Eckart theory. So again, as I said, along the gapped modes, the entropy grows. But now, if you add the second order correction given by the Israel-Stewart theory, this profile changes. Hitchcock and Lindblom have proved that to have your Israel-Stewart theory stable, you need to add this term with a b which is larger than 1. And look what happens. If you put b comprised between 0 and 1, the profiles fall here in the middle. And as you see, your equilibrium state is still a minimum of your theory. Now, when you pass b equal to 1, you start having profiles like this. Now, as you see, the entropy is maximum. It's a local maximum, because the stability analysis of Hitchcock and Lindblom is an analysis based on small fluctuations around equilibrium. So it's a local maximum, but now it's a maximum. So if you prepare your system with a non-zero gapped mode, its entropy must grow, and the system will necessarily come back to equilibrium. So this is the reason why Israel-Stewart can be stable. Now, the nice thing is that Hitchcock and Lindblom have also shown that Israel-Stewart can still be unstable if you move far away from equilibrium. And this plot shows you why this happens. Because if you move sufficiently far away from equilibrium, then you pass this minimum. And then if you are in this point, your entropy must grow. You cannot go back in this direction. You must go in this direction. So with this analysis, we have shown that all the stabilities and instability properties, both of Eckart and Israel-Stewart, are purely thermodynamical in the sense that they just come from the profile of your entropy. They are independent from the details of the equations of motion that you take. They only depend on this shape of the entropy and on, of course, on the conservation of the energy momentum and so on.
Sorry, may I ask a question here?
Yes.
So what happens if we go in higher order terms? Do you expect that this raise at the end around k equal 1 or minus 1? I mean,
what happens if we go to higher order terms?
Yes. Instead of second order, you go to third or fourth. Yeah.
Well, of course, if you add the further terms, you will have some more pieces that you will need to account for when you move more far away. In fact, for example, the Carter variational approach, which is another alternative to Israel-Stewart, for small deviations of your entropy, for small deviations of your system from equilibrium, is equivalent to Israel-Stewart. But in its structure, it's by construction non-perturbative. So it contains all the orders. Then if it is true or false, correct or wrong, it's another topic. But there are some theories which claim that they can go even more further, including third, fourth, and other terms. Now, of course, if your aim is just to know perturbative stability, the stability for infinitely small deviations from equilibrium, it's enough to go to the second order, because in the end, the second order is the typical concavity convexity principle, which gives you stability. But of course, if you add further terms, then you can refine your profile. So of course, you can expect Israel-Stewart to explode when you go far away from equilibrium, because Israel-Stewart is not designed to go far away from equilibrium. But the mathematical origin why it does is this shape of the entropy that is postulated from when you write down your equations.
So you expect that by extending this expansion up to infinity, this local maximum of entropy would be a global maximum.
Extending this expansion to infinity? Sorry, didn't hear.
Yes, expanding this infinity, the expansion up to infinity.
Yes.
Do you expect that this local maximum for entropy, turns to a global maximum?
Absolutely, absolutely.
Yes. Yeah.
Absolutely. If you improve your description of the entropy, so including other terms, of course, this you can expect this behavior to go down. And indeed, you know this from kinetic theory, because kinetic theory tells you that the equilibrium is the absolute maximum of your entropy. So you know that in the end, your physical entropy will have a global. But if you take just your equations of the Israel-Stewart and you try to extrapolate their behavior even far away from equilibrium, which is what Hitchcock and Lindblom did to derive this instability, you will find this behavior. But I totally agree with the fact that if you add other terms, this part is fixed. Yes.
Yeah, okay.
Okay. So basically, this was the essence of the paper. So I approach the conclusions, but before reaching them, I would like to make a couple of final comments. So the first comment is, which one of the two should we take? Should we follow the idea of the frame stabilized first order theories, or should we work with the second order theory? Now, as you have now understood, probably, as you see, they claim to have a different predictive power. because the first order frame stabilized theories must work in the infrared limit, while Israel-Stewart assumes that it can go also beyond the infrared limit. So the first question that you need to ask is if you really are in the infrared limit. So if you are there, then at the moment, you can have some criteria to choose among these theories. So you can choose among them using just practical convenience. Maybe it's easier for you in numerical simulations to use one or the other. Maybe you really need to have an entropy which is maximum in equilibrium, so you may prefer Israel-Stewart, or maybe you would like your theory to be strongly hyperbolic, and the first order frame stabilized theories have improved to be strongly hyperbolic, while as far as I know, Israel-Stewart is weakly hyperbolic, and we don't know if it is also strongly hyperbolic. So this is what I know. But what I would like to remark is that you cannot use really physical arguments to choose a preferred one, because along the hydromodes in the infrared limit, the two theories are equivalent. So you cannot use really physical arguments to choose when it comes really to solving your equations, because in the infrared limit, everything is the same. However, if your system is not in the infrared limit, then by construction, the first order theories do not apply anymore. In this case, either you shoot the second order approach if you assume that hydrodynamics is still possible, or if you are in a situation in which you need to rely on kinetic theory, because even hydrodynamics is not that doesn't work anymore, then you should also abandon hydrodynamics. However, I would like to make a final remark about this issue, because my personal expertise area is neutron stars. And I have recently seen a paper in which the authors who work on the frame stabilized first order theories suggest that maybe we could use these theories to model the binary neutron star mergers. Now, I would like to make a warning about this, because I work on this topic and I know the problems. I would like to warn you that neutron stars are not in the infrared limit. So even if the theory was Newtonian, Navier-Stokes would not apply. You cannot use it. And how do you see it? I will just tell you what usually happens. When you study the oscillations of a neutron star, which are hydromodes in the sense that they are pure, essentially sound waves. The oscillations of neutron stars typically are sound waves. They are some oscillations. When you make microscopic calculations, you look at the imaginary part of omega. This is what you compute from microscopic calculations, and you find that this is the formula for the imaginary part of your omega. Now, what happens if you assume that your theory is Navier-Stokes? If you assume that your theory is Navier-Stokes, then the imaginary part of omega needs to be equal to this expression. You assume that neutron star matter is purely bulk viscous fluid, because this is what usually happens. So if you have only bulk viscosity, you don't have shear viscosity. This is your expression for the imaginary part of omega. So if you want these microscopic calculations to match with a Navier-Stokes, then you need to identify these two right-hand sides. If you do it, then you find this relation for your bulk viscosity. And you discover that your bulk viscosity depends on the frequency. And this part, this dependence of the frequency, is highly non-negligible. And this problem exists also in the Newtonian theory. This kind of calculation can be made also in the Newtonian theory. The theory which describes the neutron star oscillations is not Navier-Stokes. Navier-Stokes doesn't work, because you would have a bulk viscosity which depends on the frequency. And it's actually very interesting then when you look at the various publications in the context of neutron stars, they typically come up with a bulk viscosity which depends on the frequency. So somehow they match everything with Navier-Stokes. The problem is that your real equation is not Navier-Stokes. Your real equation is Israel-Stewart, or in the Newtonian limit, its Newtonian limit, which is not Navier-Stokes. In fact, if you look at the imaginary part of your omega in Israel-Stewart, then you will find an expression of this kind. And you see that here there is a dependence on the real part of your frequency. Now, if you want to set this equal to this, so the two right-hand sides are equal, you immediately find these two identifications. So neutron star matter is the prototype of an Israel-Stewart fluid. Extended irreversible thermodynamics is necessary, but it's not only necessary because Israel-Stewart, I don't know, it's a beautiful theory for relativistic hydrodynamics. It's necessary because even in the Newtonian limit, Navier-Stokes does not apply. So if we want to summarize the message of my presentation, you can see it here. Basically, what I have told you is that the relativity of simultaneity creates new degrees of freedom which do not exist in the Newtonian theory because you have a higher order in your equation. Now, in this extended state space, the entropy can grow even if you start from your equilibrium state because of these gapped modes. If you impose the second law to hold exactly, then you are creating the instability. The only way to solve is either you break the second law along these gapped modes, and this leads to the first order frame stabilized theories, or you fix the entropy, and this leads you to the second order theories. And with this, I would conclude. Thank you for your attention.
Okay, thanks for your very nice talk. And I hope that people can hear me because I think that I'm experiencing some internet problems. But we have time for questions and discussions. Is there any question from the audience? Yeah, okay, go on, Faith.
Yes.
Okay, thank you for your nice talk. I want to ask that in the previous slide which you showed to us for the neutron
Yes.
star.
Now this one?
Yes, yes. I want to know that is there any approach or papers, I don't know, that apply the Cousteau's approach to the neutron stars? I mean, leave the Straley-Stewart approach and apply that framework to the neutron stars.
Sorry, I didn't understand. I didn't hear well. Could you please repeat your question?
I asked about the applicability of this approach which you showed to us in the framework of Cousteau's approach. I mean, the choice of frame. Did you work for that? For example, instead of applying Israel-Stewart theory to the neutron star, you apply the Cousteau's approach and did their parameters in the neutron star physics and something like that?
Well, here is the issue. If you want to apply the first order frame stabilized theories in this context, you already know that you need to go beyond the infrared limit. So the philosophical justification of the approach does not hold, is no more there. But maybe it can happen that going beyond the infrared limit, it turns out that these equations can still reproduce something like that, since the different frames behave differently when you go far away from the infrared limit. Actually, this kind of issue is something I would like to study better. I would like to study under which conditions, if you take the equations of the first order frame stabilized theories and you go beyond the infrared limit, maybe you still obtain some equations which have this kind of characteristic behavior. So I'm not excluding that it is possible still to reproduce this with those theories. What I just wanted to remark is that you cannot assume from the beginning that the derivatives are small. You can assume that the deviations from equilibrium are small, but not that the derivatives are small in neutron stars. I don't know if this answers your questions. Well, actually, I told you that still I don't have the answer, but did I understand at least the question properly?
At least, yes, approximately. Thank you.
So before I ask Farid Tarabi to ask his question, I want to make a comment on this on the question by Farid. Actually, you cannot find a first order application to neutron stars or even black holes or something like that. Yeah, for example, you can find them in my notes somewhere. But as Lorenzo just said, there are a lot of difficulties with the first order in this area. So probably people, because you know the simulations are quite expensive, and I cannot imagine that people will be convinced to use it in such a framework. I don't know. So that was my comment. Please, Farid.
Yeah, do you have any comment about the applicability of this method for heavy ion physics? Because, I mean, you already commented on neutron stars. Do you expect that, I mean, do you expect any applicability of this method in heavy ions? Because we know that Israeli-Stewart method works perfectly fine in this.
Actually, these theories, these frame stabilized, I like these frame stabilized first order theories in general. I think they are really promising if you apply them in the correct context. So once you make sure that your system has, say, small gradients, then these theories are nice because you start setting your initial conditions, and your initial conditions in general will be bad because they will include some gap modes. You wait just a bit, and these gap modes die very fast because their imaginary omega is finite even in the limit of small gradients. After a while, you say that your system goes on shell, so immediately you will have you will obtain your good initial conditions, and then you will have an evolution which is really, if you want, the philosophical generalization of Israel-Stewart to relativity. Because from a philosophical perspective, Israel-Stewart is different from Navier-Stokes. Even in the Newtonian limit, it is different. In fact, the Newtonian limit of Israel-Stewart is the Jew extended irreversible thermodynamics. So in this sense, I expect that, provided that you make sure that your gradients are small, these first order theories will work well. And they will also work well because recently they published a paper in which they showed that these theories have very good mathematical properties. Strong hyperbolicity, they tested the causality, they tested mathematically speaking, they are very well made. So I think they can be a nice tool, but I just think that it would be dangerous to go to neutron stars. And why is it so? Because in neutron stars, the big problem is that many processes which go to equilibrium are driven by weak interactions. For example, the processes which are responsible for the Navier-Stokes that are possible for the bulk viscosity here are the transformation of protons of the neutrons, which becomes protons and electrons and neutrinos, and vice versa, are beta processes and so on. They are very slow. And so even if you are in a good hydrodynamic regime, you are not in the infrared limit to have Navier-Stokes. So the thing is subtle, but I think that in heavy ion collision, it can be done once one makes sure that you are in the infrared limit.
Well, and then if we can apply it, then do you expect, for instance, we can keep the shear viscosity or other transport coefficients as a free parameter, and then extract them from the experiment. So if I start from these two different approaches, do you expect any difference measurement, any different measurement for transport coefficients?
No, they should be equivalent. Because along the hydromodes in the infrared limit, everything is the same. And the interesting thing is that you can show that all the hydrodynamic frames are the same in the infrared limit, but you can also show that Israel-Stewart is equivalent to these theories in the infrared limit. And this somehow, and this actually is quite easy to show, because basically if you take this equation, let me check here. This is the typical Israel-Stewart equation for the bulk viscosity. Now, if you are in the infrared limit, this is small, and this is the derivative of something which is already small, so it's a second order, so you throw it away and you recover this. So there shouldn't be any physical distinction, and this has also been done more rigorously by Robert Garrosh, I don't know if I am pronouncing him correctly, that has really shown that the Israel-Stewart theory along solutions that you can consider your famous hydromodes is indistinguishable experimentally from Navier-Stokes. There is this famous paper in which he shows that Israel-Stewart is equivalent basically to Navier-Stokes along these kind of solutions. So there shouldn't be experimental distinction.
Okay, thank you.
So I like to make another comment on this question. And this is that there are two problems with the first order approach. And the first one is that you cannot match the first order to any microscopic theory. I mean the regulator part of the first order. So if you want to do a numerical simulation, you don't have any clue about what kind of number you should start with for the extra transport parameters that are not physical. And since they're not physical in some sense, you cannot match them with, for example, you can actually match the relaxation time from holography or from kinetic theory, and you can have some number to start with in this Stewart approach. So essentially, this is the first problem, which is a practical problem. And the other problem is that the predictability of first order stable theory is equivalent to the predictability of Navier-Stokes theory. And I'm not sure that if for some systems you cannot find anything related to the regulating part of the Israel-Stewart theory from experiment. For example, if you want to compute the number of particles, if you use this Israel-Stewart, you will have some relaxation time dependency in your result. But if you use the first order, you need to make it on show to compare with the experiment. The third problem that is probably related to Farid's area of work is that there's an argument by Michael Spalinski that is in the audience about the regulator independency in the Schreier theory. And he finds that for the typical scale of a system must be at least larger than 1 over temperature. So let it, for example, RT is larger than 1. I hope if I'm not, if I'm wrong, Michael will correct me. But if you use the same calculations for the first order, you will find that it is like this, the minimal size of the system must be 60% larger than the MIS1, at least. This may be a problem, another practical problem.
Well, indeed, I would like to point out one thing. The idea is that you have these 16 parameters, and as exactly it was pointed out, only 3 are physical. All the others, as it was said, are not measurable because you just fix them to obtain stability in your gapped modes. And you are describing your gapped modes are unphysically because you're not treating the entropy consistently with microphysics. So really, you have 3 really physical coefficients, which are the bulk viscosity, the shear viscosity, and the heat conductivity. But all the rest is really put there just for you to fix the stability problem.
Yeah.
And once you do it, then you find that on the hydro modes, everything is equivalent to Navier-Stokes, essentially, exactly. So yes.
Okay, thank you.
They are not non-measurable.
Other questions? Or comments? So if there is no other question or comments, I can stop the recording.